Hello, everybody. How are you all? I hope you all are good and fine. So, this is me, and I welcome you in this chapter. And this is magnetic effect of electric current. So, this is lecture number first, and let me take you to the next slide and let's start this chapter without wasting our time. So, here we are. So basically, guys, in this lecture, we will firstly study about magnet. What is a magnet? Okay. So basically, since our childhood, we all know about magnet. Okay. Because let's me give you an example. Whenever we used to go a toy shop, okay, and let's suppose that we purchase a toy from that shop. So most of the children, what do? They basically destroy the toy, okay, and they open, let's suppose if they purchase a car, they simply open up the car. So what happens when you open that toy, when you open that car, or we can also take example of a radio, okay, and we can also take example, there are lots of examples we can take. So when you open these appliances, then you find out a magnet inside it. You will find a magnet inside it. So what is a magnet? So first of all, let's discuss about the definition. So magnet is an object that attracts objects made of iron, cobalt or nickel. Okay. Or I can simply say that magnet is an object that attracts iron and iron like materials. Okay. These cobalt and nickel are iron like materials. So the magnet attracts these objects. Okay. Iron and iron like material. And if I talk about what are iron like materials, then these are cobalt and nickel. Now, the second point is magnet comes to rest in north to south direction when suspended freely. Okay. So what happens, guys? There are different type of magnets. Okay. There are different type of magnet. Let's take example bar magnet. Okay. And there is also another type of magnet, and that is magnetic needle. Magnetic needle. Okay. And there is another magnet, and that is, you can say, electromagnet. Later in this chapter, we will be discussing these magnets very clearly, but for now on, you just need to remember that these are the examples of the magnets. Okay. So guys, when this magnetic needle is suspended freely, then this comes to the rest in north to south direction. Let's suppose this is your magnetic needle. Okay. So this is indicating north. Okay. It's north. And let's suppose this is south, and this is south direction. This is north direction. This is north pole, and this is south pole. Okay. So basically the north pole of this needle will indicate the north direction, and the south of this needle will indicate the south direction. Okay, guys. So now you should be confused that what are these poles, because I am talking that north pole is indicating north, south pole will indicate south, but we don't know that what are poles. So basically, let's suppose this is a magnet, and this is, we call bar magnet. So all the magnets, I'm not only talking about bar magnet, all the magnet has two poles, north pole and south pole. Okay, this is a north pole, this is a south pole, and they will always come in pair. You will not find a magnet which only have north pole. or which only have south pole. It is not possible. Okay, every time you find a magnet, then there will be north and south pole present in that magnet every time. Okay, because they always come in pair, they doesn't come alone. So guys, what happens, this is a north pole and this is south pole, and we will also discuss some other properties of these poles. But for now on, you just need to understand that whenever a magnet is suspended freely, then its north shows the direction north, and its south, or you can say its south pole, shows the direction of south. So I hope guys you understand this point. Now let's talk about use of magnets. This is also very important. So magnets are used in refrigerators, in radios. I just gave you the example of radios. Okay. Okay, and this is stereo speakers, in audio and video cassette players. I think you know about these cassette players. Okay. So guys, in all these appliances, you will find a magnet inside it. Now, what is their work and all these things we do not need to discuss here, but we just need to remember that in these appliances, a magnet is used. I hope guys you understand this. Now, let's move on to the next slide.
Here we are. Here we will have to study the properties of a magnet. What will we study here? We will study the properties of magnet. So, a free suspended magnet always points towards the north and south direction. So this is the thing which we already know, that whenever you, let's suppose this is a needle of your magnet, and if you move it freely, and you can say that if you suspend it freely, then it will give you the direction of north, and this will be south. Okay, so this will be suspended like this. Now the pole of a magnet which points toward north direction is called the north pole or north seeking pole. So basically this direction is known as, this side is known as north pole, and this side is known as south pole. Okay guys, I hope you get my point. Now let's see the pole of a magnet which point towards south direction is called south pole. Okay, and the pole which indicates this north will be known as north pole. Like poles of a magnet repel each other, while unlike poles of magnet attract each other. This is very important guys. Basically, we know that there are two poles of a magnet. This is north pole and this is south pole. So first thing you have to remember that you will not get these poles alone. They will always come in pair. Okay, because my mean to say is, if you want that I will get this north pole only, then it will not be possible. These poles will always come in pair. If there is a north pole, then definitely there will be a south pole as well. Okay guys, I hope you get my point. So here, let's suppose if I bring closer this north pole here, and this is your south pole, then they will repel each other. They will repel each other. There will be repulsion between these poles. Repulsion between these poles. Why? Because they are same poles. Okay, and same type of poles always repel each other. Had I brought closer this south and south, let's suppose this is north, this is south, and if I brought closer this south here, this is north here, so they will also repel each other. Why? Because they are same nature, they are same type of pole, same type poles, or you can say these are like poles. Okay, but instead of this, if I bring closer the opposite poles, then they will attract each other. Let's suppose this is north, this is south, and this is north, and this is south. Here, if these poles are bringing closer, are being brought closer, then definitely they are going to attract each other. Attract each other. Okay, and why they attack each other? This is their property. Okay, we cannot do anything in this. This is their property, that unlike poles always attract each other, but like poles always repulse each other. So I hope guys these 3 points are clear to you. These 3 points are clear to you. Now let's move on to the next slide and let's try to understand some other concepts. So here we will discuss about the magnetic field. What will we discuss? We will discuss about magnetic field. So the area around a magnet where a magnetic force is experienced is called the magnetic field. It is a quantity that has both direction and magnitude. It is a vector quantity. Now, let me give you a quick idea what is a vector quantity. Vector quantity. So basically guys, what happens? There are two types of quantities. First one is scalar quantity, and the second one is vector quantity. So what is the difference between these two quantities? So basically, the main difference between these quantity is that the vector quantity always have direction. Let me write it here. Vector quantity always have direction as well as magnitude. So vector quantities has both direction and magnitude. Let's suppose, let me explain this by an example, that let's suppose if you want to say that I'm going to my friend's house. Let's suppose if I want to go to my friend's house, and if I tell you that my friend house is 2 kilometers away from your house, then will you be able to reach your house just by this, if you have the knowledge of the distance? No, you won't be able to go. Why? Because I also have to mention the direction. Okay, if I say that my friend house is 2 kilometers away and in north from my house, then you will definitely be able to reach, because here you have also the information of the direction. So this quantity is known as vector quantity. And let me give you some examples of vector quantity, like velocity. Velocity is a vector quantity. Okay, and acceleration, this is also a vector quantity. Okay, but there are some scalar quantities also, okay, where you do not need to give information about direction, like 5 liter milk. So you will not be saying that give me 5 meter milk, give me 5 liter milk in north direction. No, you won't say that because you do not need any direction here. So here this 5 liter milk is what? This is a scalar quantity, but velocity, acceleration, these are vector quantity. So guys, after having information about the vector quantity, we also have to understand that magnetic field is also a vector quantity. And what is a magnetic field? Magnetic field is basically the area where you can feel a magnetic force. Let's suppose this is your magnet. Okay, now if you are here, or you can say if you place an object here, and this is made up of iron, so this will feel a force. Okay, this will experience a force. Now if you move it here, then might be they will feel a force, they will experience a force. But if you keep it far away from this magnet, then at some distance it will stop experiencing this force. So at what extent it experience force, that area is known as the magnetic field. Okay, and this is a vector quantity. So I hope guys you understand what is a magnetic field. Now let's move ahead and let's try to understand some other concepts. So here on this slide, we will discuss about the magnetic field and field lines. The magnetic field and field lines, it is very, very, very important. So basically, we have a very good idea about magnetic field. But here we have to understand field lines. So in the magnetic field, the force exerted by a magnet can be detected using a compass or any other magnet. The magnetic field is represented by magnetic field lines. Okay, so basically this is, let's suppose your magnetic field. This is the area where you can feel a force, you can experience a force. So this force is represented by this magnetic field lines. Okay, and how did we make this magnetic field lines? So by this, to understand this concept, you can also do this example, and this example is also given in your NCERT book. So let's suppose this is your magnet, this is north pole of your magnet, this is south pole of your magnet. Now let's suppose what you do, you basically take the, what do? You will take a powder of iron. Okay, a powder of iron where there is lots of small pieces of iron. And if you spread these pieces around a magnet, then it will be arranged like this. It will be arranged like this, like in this picture you can see. Okay, so this arrangement of this, the iron preparations, you can say the iron powder, is known as the magnetic field lines. Okay, so this arrangement is known as magnetic field lines. So this shows that how a magnetic field work on a magnet. Okay, and these are basically the imaginary lines. These are imaginary lines. Okay, and you can also see that this has direction as well. And what is the direction? The direction of magnetic field lines is from north to south. You can see this is going from where to where? This is going from north to south. Okay, but inside a magnet it is going towards south to north. So you have to remember this, that inside a magnet, the direction of magnetic field lines is south to north. But this outside of this magnet, outside of this magnet, it will be north to south. So this question can be asked. Now let's move ahead and let's try to understand some other concepts related to this. So we know that imaginary lines of magnetic field around a magnet are called field lines or field line of magnet. When iron fillings are allowed to settle around a bar magnet, they get arranged in a pattern which mimics the magnetic field lines. Field line of a magnet can also be detected using a compass. Magnetic field is a vector quantity. It has both direction and magnitude. Okay, so basically this is what this paragraph is saying. Basically, let's suppose this is a magnet. Okay, this is the north of your magnet. This is south of your magnet. And if you spread the iron fillings, then it will allow the iron filling to settle around a bar magnet and they get arranged in a pattern. Okay, and this pattern is what? This pattern is mimics the magnetic field lines. Okay, and it will be from north to south outside the magnet, but inside the magnet it is from south to north. Inside a magnet it is from south to north. So I hope guys you get this point. And magnetic field is a vector quantity. It has both direction and magnitude. And guys, we can also draw these magnetic field lines by the help of a compass. Okay, and how can we do that? Let me show you. Let's suppose this is magnet. Okay, and let me change the pen. So what you can do, you can simply put a compass like this. So let's suppose at this point you have kept your compass and here the compass is showing this direction. Okay, here the compass is showing this direction. So the magnetic field is in this direction. Now let's suppose if you place a compass here and now this is showing this direction. So the magnetic field lines direction will also be here. So you repeat the same process and you will get the same pattern which we got by this example of iron filling. So I hope guys you get my point. Now let's move ahead and let's try to understand some other concepts related to this. So here we will discuss the strength of a magnetic field. So the closeness of field lines shows the relative strength of magnetic field. Closer lines show stronger magnetic field and vice versa. Crowded field lines near the poles of magnet show more strength. So basically, let's suppose this is your magnet. Okay, this is north, this is south. So this is a line going like this. This is another line going like this. Okay, and this is also a line. And this is also a line. Okay, so you can see that here the distance is higher. The distance between this is larger. So this shows that magnetic field here is less. But here you can see the magnetic lines, the magnetic field lines are closer. So here you can say the magnetic field will be higher. Okay, so the closeness can be a parameter to identify the strength of a magnetic field. If the closeness is more, then the magnetic field will be higher. If the closeness is less, or you can say if they are at some distance, then the magnetic field will be lower. or you can say the strength of a magnetic field will be lower. I hope guys you get this point. Now let's talk about the properties of a magnetic field lines. So basically the first property of magnetic field line is they do not intersect each other. Okay, so here you will not be able to see any magnetic field lines intersecting each other. They cannot intersect each other. Because why? Because we know that magnetic field lines has its directions. Okay, so if they intersect, let's suppose at this point they are intersecting. So at this point, what will be the direction? You will get two directions. First one is this and the second one is this. So because magnetic field lines cannot have two directions, so that's why it cannot intersect. Okay, the second point, it is taken by convention that magnetic field lines emerge from North Pole and merge at South Pole. So here in this picture, you can see that magnetic field lines are emerging from North Pole and merging in South Pole. It is going out from the North Pole and entering in the South Pole. Now inside the magnet, their direction is from South Pole to North Pole. And inside this magnet, you can see that the direction of these lines is from South Pole to North Pole. Therefore, magnetic field lines are closed curves. This is very, very important. So let me take you to a previous slide. Okay, so in this slide, you can understand that magnetic field lines are going out from the North Pole and entering in the South Pole, and they are basically completing a closed curve. They are completing a closed curve. So that's why we are saying that magnetic field lines are always having a closed curve. I hope guys you get this point.
Okay, guys. So we are here in this slide, and in this slide, let's read it out. Magnetic field lines due to current carrying state conductor. A current carrying state conductor has magnetic field in the form of concentric circles around it. Magnetic field of a current carrying state conductor can be shown by magnetic field lines. The direction of magnetic field through a current carrying conductor depends upon the direction of flow electric current. Okay, so basically guys, let me cut it short for you. The language is a little bit difficult, but I'm here to make it easier for you. So this is saying that, let's suppose this is a current carrying conductor. Okay, and current is flowing here in this direction. So we know that current carrying conductor has its magnetic effect, because current has its magnetic effect. Current has its magnetic effect. In the previous lectures, we saw that electric current has its heating effect also. Okay, whenever you pass current across a conductor, a wire, it will heat up. Why? Because of the heating effect of electric current. Now, current has magnetic effect as well. And we also know that a, around a magnet, there are magnetic field lines. So if this conductor having a current in this direction, if due to this current a magnetic field is generated, then definitely there will be a magnetic field around it. Okay, so what happens guys, we want to identify the direction of those magnetic field lines. Okay, so what do we do to find out this direction? What do we do, guys? There is a rule. Okay, and I will tell you the rule in the next slide. But let me tell you what happens when your current flows in this direction. So basically, the magnetic field lines will be like this. It will be like this. The direction of magnetic field lines will be in this direction. And this is called anti-clockwise. Anti-clockwise direction. But what if I invert the direction of current? Let's suppose current is flowing in this direction. Now what happens? The direction of the magnetic field will also be changed. It will also be changed. Now in this case, when current was moving upside, the direction was anti-clockwise. But here in this case, what will happen? The direction will also be invert. The direction of magnetic field will also be invert like this. Okay. So this will be the direction. Now let's move ahead. So guys, it is very difficult to find out the direction because we have to do two things. Either we have to by heart the direction or we have to apply some logic. So basically there is a rule which we call right hand thumb rule. Okay. And by the help of this rule, we can easily calculate the direction, or we can say we can easily find out the direction of magnetic field lines. So let's talk about what is this rule about. So let a current carrying conductor be suspended vertically and the electric current is flowing from south to north. In this case, the direction of magnetic field will be anti-clockwise. If the current is flowing from north to south, the direction of magnetic field will be clockwise. So this is not some other information. We already know this, that whenever current flow from south, let's suppose this is south, this is north. If current is flowing from south to north, then the direction of magnetic field will be anti-clockwise. And now for your simplicity, let me give you a trick, because most of the student get confused between anti-clockwise and clockwise direction. Okay, so let's suppose when you talk about anti-clockwise, then first of all you can see that n is coming. This is a trick. You do not need to take it on seriously. This is just a trick. So n is coming, so that's why you have to make an n like this, and you have to round it across the corners. Okay, so this direction is anti-clockwise. But when I'm talking about clockwise direction, so you have to make S. Okay, and you have to curve this S through the corners like this. Okay, and this direction is clockwise direction. So this is just a trick to remember what is anti-clockwise and what is clockwise. So guys, let's talk about this right hand thumb rule. So basically, to apply right hand thumb rule, what you have to do? You have to simply keep your left hand in your pocket. Okay, because guys, what happens whenever we give exam, so we can use left hand instead of using right hand in our examination. So this can make your question wrong. So first of all, you should remember that we should not use left hand rule, okay, to apply this rule. Okay, make sure that your right hand is outside and you are applying this rule by your right side. So what is this rule about? So basically, in this rule, what you have to do, you have to keep your hand like this. Okay, and you have to keep your thumb straight, and you have to keep your fingers curved like this. Okay, so let's suppose this is a current carrying conductor, and you have to find out the direction. Okay, so what do you have to do? You have to imagine that you are holding this conductor in your right hand, and your straight, you can say your straight thumb is showing the direction of the current. You have to keep your thumb in the direction of current. So if you keep your thumb in the direction of current, then your fingers will be showing the direction of magnetic field lines. So this is our rule about. So basically, let's suppose this is a current carrying conductor. Current is going from south to north. So you have to keep this thumb. This is your thumb. You have to keep this thumb in the direction of the direction of current. So these fingers will be showing the direction of the magnetic field lines, and in this case you can see that these lines are anti-clockwise. Okay, now I hope guys you understand. Now if I invert the direction of current, then what will be the direction of magnetic field lines? Let's suppose here in this case the current is flowing from north to south. So you have to invert your thumb as well. Your thumb will go downside, and your fingers will be curving like this. Your fingers will be curved like this in this direction, because you are now you change the position of your what? Right hand. You are holding a conductor in your right hand, but because the current is going downside, so you have to keep your thumb in the direction of current. So you also have to take your finger, sorry, to take your thumb downside, and in this condition your fingers will be like this in this direction, and this is what? This is clockwise direction. Clockwise direction. I hope guys you understand this. This is very important concept. That's why I'm emphasizing on this rule, because lots of questions are asked on the basis of this rule. Now guys, let's move to the next slide. And here is an example. Examples are very important. So let's talk about this example. So basically in this example, what do we have to do? We have to find out the direction of current in a straight conductor if magnetic field lines are clockwise. Okay, so what do we have to do? Let's suppose this is an conductor. Okay, and now what is happening in this conductor? The direction of the magnetic field lines is clockwise. Okay, so what do you have to do? You have to keep your fingers of right hand in this direction. And when you keep your fingers in this directions, then your thumb will automatically go downside in this direction. Okay, downside in this direction. And make sure that your thumb is straight. Okay, so now guys, what happens when you keep your right hand like this? Then this thumb will be showing the direction of current. So it means the current is going from north to south. And we also saw this in the previous slide as well. When the current was going downside, then our fingers will be in clockwise direction, and that is the direction of magnetic field as well. Magnetic field direction. So I hope guys you understand this point. Now let's go, and now this lecture is over, and I will see you later lectures. Bye bye guys.